So, Anna, thanks very much for being with us today. It's a pleasure to host you. Anna is going to talk today about human performance during space exploration. Anna, she studied aerospace engineering at UPM in Madrid, and with a combined degree with Super Aero in Toulouse. Then she got a Fulbright scholarship and moved to the States, where he got a PhD at the MIT in 2015, where she studied the artificial gravity combined with exercise as a countermeasure for space flight related physiological deconditioning. So she's kind of bridging aerospace engineering and biomedical engineering, which is a quite interesting topic, looking into human space exploration. She has also been Amelia Earhart Fellow, among other awards, and now she is directing the Bioastronautics and Human Performance Lab at Texas A&M University in the States. And just to finish, I would like to mention that she's going to do a 1-year sabbatical next year in Madrid, and we might have the opportunity to collaborate with her, so please stay tuned with what she's doing, and don't hesitate to ask for a meeting afterwards or whatever. So Anna, thanks very much. First yours.
All right. Well, thank you very much, everybody. I'm really excited to be here today, talking to you a little bit about what I do here. So thank you, Manuel, for the introduction. So I typically start with here you go with this slide, but I guess you did a great job already. As Manuel said, I am a traditional aerospace engineer, and when I do this, when I talk to students, I always like to emphasize that, because you will see the kind of things that I do perhaps you could think that traditional engineer, like, what are you doing these things? Is your background biology, or are you a med school, or things like that? So I'd like to emphasize, no, I'm a traditional engineer, and also I worked for 5 years in operations, launching rockets, Ariane 5 rockets in French Guiana. So that was in my previous life before going back to school and do a PhD. So again, maybe this is more for students, but what you do right after school doesn't have to be what you do forever and ever. And for me, I thought that was the best job in the world. I was launching rockets, like my dream. And somehow there was this human aspect that I was missing. And that is what made me eventually quit my wonderful job and go back to school, which was an interesting transition for sure. And I was really lucky to land in a lab at MIT where still was an aerospace engineering department. So I felt very grounded, but also this lab was studying all these things of human performance and human factors, human physiology. And that's where I got really outside my comfort zone to start studying some of these issues that I was really passionate about and just wanted to pursue. So that's a little bit of my personal take on where I am. But after that, I went to Cornell for a couple of years. My husband got a job there as a professor. He's also from Spain, and I think he will be giving a talk soon. He's also coming on sabbatical, obviously, the whole family. So I went to Cornell because he was there, and then we moved to Texas A&M a few years later because I got a job at A&M that was good for me. So again, emphasizing this two-body problem or two-body opportunity that some of academics and maybe some of you also have to consider and play with. So for us, it ended up working really well. We have been at A&M since 2018, and here I run the Bioastronautics and Human Performance Lab, and that's what I'm going to be talking to you a little bit. So this slide attempts to summarize a large part of my overall research objectives and hopefully provide an overview of some of my past and ongoing research projects in this particular research area. So one of my main objectives is to understand how altered gravity environments affects human performance. So in the figure in the beginning, let me see if I get highlighter. Nope. Laser pointer. Okay. In this figure at the center, you can see what we call a generic dose response curve of a generic human performance response. So let's say this is, for example, a cardiovascular response, just to get us on topic, but it can be any other type of response. So generally, we know what that response looks like in 1G over here because we have been on Earth for a long time. And more or less, we have a sense of what this response looked like in 0G, just based on all the 50 plus years that we have been in space. However, we know very little what happens in between, including the shape of that particular response. And that is very important for two reasons. First, we want to know what are the effects of partial gravity on human performance, and in particular, the moon or Mars, or more generally, any other G level. But second, if we want to develop effective countermeasures, we need to know what are these gravitational thresholds that are needed to maintain an acceptable level of performance. So for example, in the figure, we can see Mars gravity over here. And if our response look like the green line, for example, we could envision, well, my response is going to be very similar to my response in 1G, so perhaps I don't need to do anything about it, or I know I'm going to be in relatively good shape. However, if the response look like the red line over here, we might actually need to do something about it, because perhaps that response is not going to be acceptable. So these can drive some of the operational decisions and countermeasure development when we think about other gravitational environments. So a large part of my research is to develop or generate these dose response curves, and not only in hypogravity between 0G and 1G, but also generally, hypergravity as well. And we can think about pilot performance in high G environments and things like that. Another interesting question for me that is not necessarily reflected in the picture is the idea of adaptation. So this response, this picture that we have, could evolve over time. And this is something that I'm also very interested about. So as you can see from some of the pictures, a domain that I'm very particularly interested is related to cardiovascular responses. And you can see some of my projects, hopefully on this domain, including centrifugation in figure 2. So that figure comes straight from my PhD back then. Or and now we're using also other testing environments. You can see down there at the bottom of the screen. So we use a lot things like tilt paradigms, like this picture is representing. So when we tilt somebody, we could mimic some of the effects of being in an altered gravity environment just based on the fluid shift that people experience, and we'll get to that. But it's a very well-accepted analog environment to study cardiovascular responses in altered gravity. The second picture here is representing something called the LBMP, lower body negative pressure. This is where I'm going to focus my talk after this slide and some of the studies that we have done with this device. And in case you have never heard about this is very simple. People put their lower body inside the chamber and we create negative pressure. And this, what it's going to cause is a fluid shift towards your leg. So it's creating an orthostatic stress, but it's something that you can manipulate because you can choose how much pressure you want to put in there. So it's another way to manipulate orthostatic stress and study these kind of responses. And then on the right, you can see another centrifuge. This is a centrifuge that we have here. Texas A&M, that it's almost working, not working yet, but it looks great. But hopefully we can start some of these studies with centrifugation soon. So I will be expanding on this cardiovascular area in a minute, but also mentioning that I'm interested in other physiological systems as well, including sensory motor, vestibular responses, and musculoskeletal and metabolic responses. So figure 4 at the top is representing a NASA-funded project where we were studying bimanual coordination in partial gravity, and we were lucky to go into parabolic flight almost 2 years ago to study some of these responses. And then here at the bottom, I think I have a little video. Here, this is a study that we have been conducting the past few years using a partial gravity treadmill to study metabolic responses in partial gravity, and then use some of that data to develop metabolic modeling for planetary exploration and planetary traverses and things like that. So this can, if we think more about the technology development area, we are taking these models and try to create, for example, path planning tools that allows you to go, from point A to point B, but instead of what's the faster way, you can say what's the most efficient path based on terrain, individual characteristics of the subjects, and all sorts of other things. So this is ongoing work that we're working in here. So generally, as you can see, I do a lot of human experiments, but also we try to stop this. We also try to model everything that we do as well. So this is where the engineering background also comes very handy. And in my lab, there is room for lots of different backgrounds of students too, in that sense. So generally, there are all these different projects, but the underlying question is always the same. What's the impacts or the effects of gravity? What are the underlying dose response curves? And how can we use this information to design better countermeasures to ensure human performance, health, and safety during space missions? I know that was probably relatively long summary, but since probably you weren't aware of what I do or my lab, I thought I would take some time to tell you a little bit more the kind of things that I do, that I'm interested in, and also for future collaborations for next year. All right, so with that, I'm going to jump into some of the projects. This is a NASA-funded project that we have been working on related to the cardiovascular responses. So generally, astronauts experience many physiological changes in space, but I'm going to focus, as I mentioned, on the cardiovascular deconditioning. What happens is that when we go to weightlessness, or 0G, as we call it, the hydrostatic pressures in our body are going to get removed. They are not going to be there anymore. And you can see a really famous picture from Alan Hargens. It's very famous in our fields, and we can see how typically when we are standing up, we have accumulation of fluid in the lower body just because of gravity. And then when that gets removed, this fluid is going to get redistributed a little bit. And then the pressures across our entire body are going to equalize. And then we are going to see, a more puffy accumulation of fluids, higher pressures in the upper body over here. Those pressures are not necessarily pathologically elevated, but what happens is that they are constantly there because postural changes doesn't happen in space. Here on Earth, we get up and then we go to bed, and we get up and we go to bed. So we see all these changes happening often. In space, that doesn't happen. So we think some of the issues that I'm going to keep talking about are related to this idea that postural changes don't occur in space. And some of the direct consequences of these changes are listed in the slide, and they include decreasing blood volume, cardiac atrophy, decreasing aerobic capacity, and also, as I was saying, a very congested upper body. So we see astronauts with this puffy face, facial edema. They experience venous engorgement, and also sometimes increasing intraocular pressure, which is going to become important in the next few slides. If you guys have any questions, please feel free to interrupt at any time. I'm happy to answer. So what I call the even worse consequences are listed in this slide and then the next one. First, astronauts experience orthostatic intolerance when they come back from Earth after spending time in space or in weightlessness. The exercise programs, they do a lot of exercise and they have become better. So people are coming back in a slightly better shape than before. But still, most astronauts require multiple people to get them out of their space vehicles after landing. And we don't know how people will react to Mars gravity in the future. We could argue, well, Mars gravity is lower, right? So they are going to be fine. But at the same time, first, we don't know that. And second, they won't have any support when they land. Typically, they have 50 people around to get them out of the vehicle. So again, the importance of generating these dose response curves. So ideally, it would be great to know what happens when we go to Mars gravity, for example. The second big issue that is happening is that many astronauts are experiencing ophthalmic abnormalities after their space flights, typically after long duration exposure of long duration space flight. This is called SANS, or spaceflight Associated Neuro-Ocular Syndrome. And some of the manifestations of SANS include disc edema, globe flattening. You can see that perhaps here in this picture a little bit better. So that's going to create some changes in vision, hyperotic shifts, and some other things. So interestingly, after, I would say, almost 10 years, we still don't fully understand why this happened, or the mechanisms, the actual mechanisms or pathophysiology behind SANS. But the main hypothesis is that it's related to this fluid shift that we're seeing, that I was talking about, that occurs in microgravity. So SANS has become one of the main red risks in the NASA Human Research Program, which is the program at NASA that studies these things. And then finally, what I would say it's probably the most pressing issue these days. We have seen a stagnant and retrograde flow in the internal jugular vein. And this comes from a study of cohorts of 11 astronauts, and 6 of them had issues with their internal jugular vein flow. So for those of you who are not familiar, the internal jugular vein are these drainage pathways. We have 2 that bring the blood down from the head to the heart. So this is the direction that we want the flow to go. And here in this picture over here at the top, we're seeing a normal flow. Hopefully you can see a yellow line over here. So as long as the flow is below that line, that means it's going in the right direction. This is what normal flow looks like. And then here at the bottom, this is an example of some of the flow that has been recorded from astronauts in space, which is highly disruptive, going in the wrong direction, very stagnant, or even, as I mentioned, going in the wrong direction. And then what's even more dangerous is that one astronaut, at least one astronaut that has been disclosed, developed thrombosis in the internal jugular vein. So now we're talking about life-threatening situations that have to be treated immediately. So because of this reason, now, this topic kind of has become a little bit more upfront, and everyone is paying attention to some of these cardiovascular issues that we're seeing, because now we are not talking about, oh, I cannot see very well, use these glasses and you'll be fine. Now this is really serious, and we were lucky that in the ISS they had some medication for some other study back then, and they were able to use that until they were able to send more medicine and up there. So really, really serious incident, and as I was mentioning, that brought to the attention what can we do about it, and what are the potential countermeasures that we can use. So given the current knowledge, countermeasures focused on bringing back those hydrostatic gradients and reducing these headward fluid shifts, all of a sudden, not all of a sudden, but have become more interesting maybe than a few years ago. For example, centrifugation and LVMP. However, going back to the dose response curves that I mentioned before, we don't really know what's the right dose that we need to apply to generate the desired response. We know we need to bring things back down, but how much pressure do you need? How much centrifugation? How much of anything? And we don't know. And specifically, we don't know in the upper body and around the eye, which is the things that we're interested based on the issues that I mentioned before. So that's kind of the motivation for these projects. And I just wanted to highlight that even NASA Human Research Roadmap, which is this framework that NASA has to basically capture all the risks and gaps that we need to answer to deal with some of the human health risks in space. And they were specific risks, just focused on some of these questions that were there, and that's where my project comes in. All right, so based on the previous motivation that this is one of the NASA projects that we have been working on, and the objective is to generate acute gravitational dose response curves of cardiovascular and ocular variables using two different approaches, both experimental approach and then computational approaches too. As I mentioned, we always like to model everything we test. So in the experimental approach, we propose to conduct 3 different experiments using 3 different interventions: tilt table, LVMP, and centrifugation. The idea was to use the same subjects across the 3 experiments, so we were able to provide a unique comparison between those interventions. Then the reality is different, but I'll get to that. So from the tilt experiment, we proposed to tilt the subjects at different tilt angles, which represent different ultragravity environments. And in each one of these tilt angles, we proposed to collect a battery of cardiovascular and ocular metrics that I will describe in a second. So we could create this gravitational dose response based on a tilt paradigm. And then we proposed the same with LVMP, in this case from 0 millimeters of mercury to minus 50 millimeters of mercury. And we did this experiment both in supine horizontal and also supine head down tilt. So this is, your head is going to be down 15 degrees compared to your feet. And that's going to create this headward fluid shift that it's mimicking what happens in space. And then finally, we are still planning, because we haven't done this yet, to do a centrifugation study, again, to look at all these different G levels and collect the data to recreate the dose response curves. So this study is ongoing. We have conducted both the tilt study and the LVMP study, not the centrifugation one. And what I'm going to focus today is on the experiment 2, the LVMP, just to give you a sense of what the kind of data that we are getting and what can we do with it. All right, so in terms of methods, we tested 24 subjects, 12 males and 12 females. I'll show you more pictures later, but hopefully you can see what the experimental setup looks like. You can see this picture in particular is showing a subject at the 15 degrees head down tilt position. And the protocol that we did with the LVMP, as I mentioned, is a graded protocol from 0 to minus 50 millimeters of mercury. So this is what the protocol looks like. We exposed the subjects to all the different pressure levels. We waited a little bit at the beginning to get steady state. And then at each one of those steady state, we collected all the data, all the dependent variables that I'll describe in a minute. Subjects came twice to do the experiments. One time they did it in supine, and another time they did it in 15 degrees head down tilt. Again, the motivation for that is to get a little bit of a headward fluid shift towards the head and the upper body. And then that would allow us to see what's the difference between those two. In terms of measurements, as I mentioned, we collected a lot of data from different cardiovascular parameters. Without going into too much detail, we collected what we call systemic hemodynamics. These are things like heart rate, blood pressure, stroke volume, cardiac output, total peripheral resistance, that sort of thing. The same device, we use a FinaPress device, for those of you who are familiar with that. It's non-invasive. We also collected all the metrics related to heart rate variability. And so subjects also had an ECG. This device has an ECG, so you can collect that from the heart rhythm. So lots of metrics related to cardiovascular control. And then finally, some variables related to the eyes and the neck, because these are the things that are going to help us solve, or I guess understand better the mechanisms of those issues that I was mentioning before. So we collected intraocular pressure. This is IOP, and this is what the ophthalmologist takes when you go to the doctor. That's the pressure in the eye. And then we collected characteristics both from the internal jugular vein, so that's again the vein that we have here on the neck, and also the common carotid artery, which is just the artery that goes up. So the artery goes up, and then the vein goes down. So we collected areas of those things, and also the pressure in the internal jugular vein with a specific device that we can collect pressure or estimate pressure, I guess. Everything is non-invasive. And then finally, something interesting is this flow pattern, right? I mentioned the retrograde flow and show you some of the pictures. These are the pictures that we collected from our study. These are things that, again, come from my lab. This is data from subjects. And we use a classification mechanism similar to what NASA did in their data, their study. This is very hard to measure. So basically, you classify these between grade 1 and grade 4. Grade 1 means forward flow that never returns to zero. So this is normal, all good. Again, below I guess this is a green line over here. This is what we want to see. Grade 2 is still forward flow, but that might return to zero sometimes. This is still considered normal. Some of us have this type of flow when we are lying on bed, so that's still good. Grade 3 is what we can consider a stagnation. So you can see how this could be really bad from creating a thrombo. And we did see some grade 3 in our data. Grade 4, which we don't have and we didn't see in our study, that means retrograde flow. So that's really flow going in the wrong direction. So that's how we treated this particular variable over here in terms of classification between grades. Just a few pictures here so you can see a little bit more what the experiment looks like. That's the LVMP chamber that we have. The middle picture is showing a subject in a supine position or 0 degrees head down tilt is typically how we say this. Excuse me. And then the picture on the right is the subject in 15 degrees head down tilt during that particular condition. So I just want to show you some examples of the data, just so you have a sense of what it looks like. These graphs in particular are not especially pretty. Again, the point is to show you, that's the kind of data that we got. In this particular case, we're seeing 3 different variables that I've been talking about: internal jugular vein area, internal jugular vein pressure, and IOP, which is intraocular pressure or pressure in the eye. And then in the x-axis, you can see the different levels of LVMP, from 0, which is no negative pressure, I'm not doing anything with the chamber, and then I'm increasing the negative pressure over here, so the orthostatic stress is higher, and then I'm pulling more blood down towards the feet of these individuals. So generally, we can see that all these variables decrease with LVMP, which is a good thing. That's what we wanted to see. Again, we have different conditions here. We have supine, -15, head down tilt. For some of or I guess for the 3 variables here, we have both left side and right side. So we collected both sides. And also we have males and females too. So that's why it looks a little ugly. But generally it goes down, which is great. So, but it's not only now I know it goes down, now I can quantify how much it goes down. And that is going to help us to create this framework to see how we could use this as a potential countermeasure. And I'll get to that in 2 or 3 slides. So these results were very positive, and we didn't see this with all the variables, but we saw this with some variables. So this is where hopefully you're already seeing how the application of this as a countermeasure is going to be tricky. In a sense, it may work for certain things, but not for some other things. And that's where this framework can help us understand better. And some other things that we did with this data was to look into the effect sizes. And in this case, for this LVMP study, we developed this Bayesian framework. We did this multivariate framework, and all kudos to my student here who did all the work. We looked into the effect sizes of all these different factors on the dependent variables or cardiovascular variables. So this is how we can read this graph. In here, we are seeing the different effect sizes of all the parameters that we collected that are listed here in the y-axis. And then in the x-axis, we're seeing that normalized effect size with negative pressure. So for example, if we look at this parameter over here, this is total peripheral resistance. That's this idea of when the body contracts to try to keep your blood up because you're experiencing certain orthostatic stress. So what this is saying is that when we increase LVMP pressure, total peripheral resistance increases. That's what this means. Heart rate, for example, that is here, we can see that with increased LVMP pressure, heart rate also increases, but increases less than total peripheral resistance. All right. If we go on the other side of the spectrum, we can see cardiac index. This is an index related to how much blood you pump from your heart. So in this case, we see that if we increase LVMP pressure, cardiac index decreases. Or this one, for example, cardiac output. If we increase negative pressure, cardiac output decreases, but it decreases less than cardiac index. So we can order all the effect sizes from the most positive to the most negative. And then here in between, something that we see here in these 2 lines, these variables fall within the ROPE, which means region of practical equivalence. And this is the equivalence of not being statistically significant. If we think about a more traditional statistical framework, these variables, we would say they don't change with LVMP pressure. These ones over here, they increase. And then these ones over here, they decrease. But then we have a quantitative sense of how much they increase or decrease. We can do the same thing with all different factors. For example, position, that's another one of our factors. So same idea, when we change somebody from 0 degrees supine to 15 degrees head down tilt, we see that, for example, the area in the internal jugular vein is going to increase a lot. IOP, intraocular pressure, is also going to increase, but it's going to increase a little less than the area of the internal jugular vein. And then hopefully you got a sense of how to use this framework and how it works. So of course, all this is normalized, so we can compare effect sizes to one another and things like that. So again, this comes from this multivariate framework, and then we can use these effect sizes to see how we can use LVMP more operationally. So this is all great, but now, I'm an astronaut and I just want to see how can I use that to help my astronauts, right? So if we think about this operational application, for example, we have seen that LVMP generally can effectively counteract that fluid shift that we see back to supine. When we are in 15 degrees head down tilt, we applied LVMP and we can bring those values back, like if you were in supine position. And then now we have all the numbers to really calculate how much do we need. And then, surprise, surprise, which you probably already got to that conclusion, it depends what variable are you looking at. So generally for variables related to the systemic and autonomic indices, the values that we need are going to be between minus 3.7 to minus 23.5. And you have all the variables here. So for example, for heart rate, if we are in a 15-degree head down tilt position, we would need 13.9 millimeters of mercury of negative pressure to bring heart rate to supine position. And then that's how you would read this graph over here. More interestingly, to the kind of questions that we are talking about today, for the head and neck, we need, for example, around 30 millimeters of mercury to bring IOP back to supine levels. And then related to IJV area, minus 45, which is pretty high. Pressure around 30, and then flow around 14.7. So this is already giving us specific values that you can say, this is how much pressure do you need to recreate. There is a caveat though. Typically when we talk about microgravity and these fluid shifts, the fluid shift towards the upper body, the way we try to recreate that on Earth is not using 15 degrees head down tilt. Typically we use 6 degrees head down tilt. So it's a little bit more subtle than 15. We just decided to go with 15 because, many reasons, but there wasn't that many difference between 0 and minus 6. So we just wanted to go with something a little bigger that also gave us a little bit more of an envelope to play with. But doesn't mean we cannot do the exercise and actually use our tilt data. Remember I talked about we had this other experiment with tilt. So we do have the tilt data and we can combine that data to see, how much we would need for, instead of 15, it's only 6. And this is presumably way more relevant to spaceflight. So the good news is that we get a little bit more reasonable values for LVMP. For example, for systemic and autonomic, we see minus 1.5, which is obviously very reasonable, towards 10. And then related to the head and neck, and again, we don't go over 20 millimeters of mercury, which again is great. Because if we go to values really, really high, we can have issues with people passing out and having syncope and things like that. So again, I think these values are pretty much the first recommendation ever that anyone has done to look into LVMP as a potential countermeasure for some of these issues that we see in space. There are a couple of caveats though, or I guess one particular caveat. And I know I haven't talked much about OPP, ocular perfusion pressure. This is another metric that is related to the eye, and I don't want to get into much details about it, but we think, that's ocular perfusion pressure. That's the pressure that the eye, that the blood kind of gets into the eye towards the back, and it's the pressure that the blood perfuses the eye. And we also think this is an important parameter in SANS. We don't fully understand what the role is, but one of the takeaways from this study is that this parameter actually does not go down with LVMP, and it's just because of the way it's calculated. Calculate this difference with the pressure at the level of the eye minus IOP. So IOP goes down, but also mean arterial pressure at the level of the eye also goes down, which makes OPP just stay constant pretty much. So if ocular perfusion pressure is a big driver of SANS, LVMP is not going to solve it because LVMP doesn't change ocular perfusion pressure. So that's also one of the bigger takeaways that we got here. So just to start wrapping up a little bit, with LVMP, we saw that it seems to be a really effective countermeasure to counteract that fluid shift that we see in microgravity for most of the variables. We generated these dose response curves for a really large set of cardiovascular variables and ocular and neck variables. And we have this modeling framework that now we can use to quantify the effects of LVMP on these headward fluid shifts. Then I guess I just summarize here again some of the values that are very reasonable for 6 degrees head down tilts. And as I mentioned, some of these variables, such as ocular perfusion pressure, are not responsive to LVMP. So we don't know what that means yet for SANS. And then again, zooming out, this is part of this larger study where we are looking into tilts, LVMP, and also centrifugation. And what is really interesting, hopefully we'll get this in the next year or two, once we get the data from centrifugation, we are going to be able to compare LVMP versus centrifugation. And everyone have talked at some point about artificial gravity, but we haven't been able to implement this in space. So really interesting comparison that I'm looking forward to see how that turns out. And then I didn't have much time today to talk about computational modeling, but we have a bunch of models just trying to model some of this. Limitations and future work. So one of the biggest limitations of this work is that we did everything on Earth, right? And then we cannot get rid of gravity, unfortunately. So we kind of assume that being in a supine position, like this little guy over here, is like being in space because you don't have gradients along the GC axis. So we said, okay, right, this is like microgravity. Let's go with it. But in reality, when we are in true microgravity, there is a big difference, and certain things changes a lot. For example, the pressure in the venous sides, the venous pressures decrease a lot in microgravity. That was an unexpected measure, but we discovered this a while ago in the field. And then, it may be possible that all this framework that I just spent an hour telling you about is actually not really representative of what happens in microgravity. So we would love to do this in parabolic flight, in true microgravity conditions. And I was really lucky to get some parabolic flights coming up to be able to pretty much repeat the study in microgravity. And I take the time to tell you this because this is the project that I've been focusing on next year. And it just happens that I'm going to be in Spain, which is great. And the flights are in France with AEROSPACE. So it's going to be actually very convenient. But I will be actively working on these projects, trying to get all this up and running. And we need a new device that is compatible with the flight and all the constraints that they have. So I don't know if you guys are familiar with parabolic flights, but if you are, they have all these rules and constraints and requirements and all that. So hopefully our first campaign will be in September this year. And we have four parabolic flight campaigns. So we will be working on this for a while to just get a bunch of subjects there. All right, and then just to wrap up, and we have some time for questions. The experiment 3, I guess we haven't done it. I already talked about this. We're working on it, and just to emphasize a little bit that the modeling approach, we do a lot of modeling and simulation of physiological systems, and in particular, we have been working a lot with cardiovascular modeling, and we have several projects working active projects right now to look at different models. We have models to look into gravitational physiology, as you know, the kind of things that I just talked about, and we try to model all those things. We use a lot lamp parameter models. So we model the entire cardiovascular system with different compartments, and we have control systems going, which are representing our physiological control systems, baroreceptors, and stuff like that. We are also looking into this question of individual differences. This is a huge thing in the NASA community, and I'm sure in others too. How can we, first of all, understand why responses in subject A are different from responses in subject B, but also how can we predict those responses so we can treat you better, or we can help you better when you go to space? Are you going to be more susceptible to SANS or some of these issues? And if yes, maybe we should be more proactive in terms of countermeasures or exercise or whatever we want to do it. We are also working with Lockheed Martin in some questions related to operationally relevant scenarios, where the war fighter and how pilots in particular, they are subjected to a bunch of G-forces, and how can we use that data to feed into maybe artificial intelligence and algorithms that we want in the cockpit to help the human, as a human machine teaming algorithms, that sort of thing. It's really hard to collect the data. So models in this case become really, really interesting to create huge databases so they can use that for their machine learning models and things like that. And then effects of hypoxia and some of the things we're trying to model as well. And with that, I'm wrapping up, just acknowledging certainly all my students, but in particular, Rich Whittle. He has been the one running a bunch of these experiments that I showed you. He graduated actually last year, so some of these data are a little old, but he's now an assistant professor too. So I'm really proud of him, doing great, and some other students and NASA for the funding and all that, and just a picture of. I have to update the picture. There has been some turnout in my lab, but just is the one that I have to date. So with that, I'm happy to take any questions from anybody. Thank you.
Thank you very much. And I don't know if we can clap or not, but well, I clap. This online, we are not used to. Okay, this clapping, like with exactly like this. Oh no.
Hopefully that was okay. I know this is very different from the kind of things that you do.
Yeah. It's true, but I mean, it was. We typically don't do online seminars, but in this case, because you guys, of course, are at the States, and you are going to come here, and I think there is a good opening for collaboration, and well, what you have just talked today is fascinating. I mean, it's you're talking about space exploration. We have in front of us, the moon colony, trip to Mars, and it has also some links with human evolution to some extent, what type of adaptation. So I think it's fascinating. Falls totally out of my domain of expertise, but still quite fascinating. And I'm sure some of the guys here in the audience are going to be talking about models because they are experts on doing modeling. So I give the floor. I mean, if Oscar has his hand raised, but if you also want to pose a question, please raise your hand, and then I'll give you the floor in a second. So Oscar, please go ahead.
Hi Anna. First of all, congrats on the talk. Very interesting topic.